So here I have this exact differential equation that I introduced in the previous video, and in this video I'm going to solve it. So the first thing I mentioned that you should do when you're solving an exact differential equation is, first of all, to verify that it's exact. Otherwise you really don't know if it's exact. So this function right here is what I would call my m of x, y, and it's being multiplied by dx, and I'm adding it with n of x, y, which is being multiplied by dy, and all of it is equal to 0. So first thing I'm going to do is I'm going to take my partial m with respect to y. So my partial derivative with respect to y of m would be equal to the partial with respect to y of cosine x minus partial with respect to y of x sine x plus partial, let me fix that plus sign there, looks terrible, partial with respect to y of y squared. And all of these terms, this cosine x and this x sine x, they go away, but this y squared stays. It becomes 2y when I take the derivative of that with respect to y, just like any regular derivative. And now let me take my partial n with respect to x, and that is equal to 2y, because that's a constant, times the partial derivative with respect to x of x, and that's just 2y. So let me go ahead and circle these two right here in green. There you have it. These two are equal to each other. 2y equals 2y. So therefore partial m with respect to y equals partial n with respect to x. Alright, so now that I've proven that the differential equation is exact, the next step is solving it. So the sticker of these two functions right here is clearly this function that I'm underlining right here. This cosine x minus x sine x plus y squared with respect to x is clearly a little bit harder to integrate than this 2xy with respect to y. If I integrate the 2xy with respect to y, 2x is a constant, and then integrating y with respect to y, that's a simple exponent rule. So that's not going to be very hard at all. But this cosine x minus x sine x plus y squared with respect to x, well, I've got an integration by parts right here. So that's clearly a little bit tougher to integrate. So I'm gonna do it this way. And there's a very interesting thing I'll notice actually when I do it like this. I'm not gonna spoil it 100%, but let's just say I might not really have a constant of integration. I'll have one, but at the same time I won't, if you get what I mean. So this integral right here, this cosine x minus x times sine x plus y squared dx. Well, the hardest thing to integrate, and I'm going to go ahead and work this out to the side, is this x sine x, which is an integration by parts. Luckily, I've got a polynomial, first degree polynomial, and a trigonometric function, so I can clearly use the tabular method. x1, 0, sine x, cosine x, and let's see, the integral of sine x is negative cosine x, and the integral of negative cosine x is negative sine x. And if you're not familiar with the tabular method, I've got a whole series on integration by parts that you should watch, and I've even got a proof of the tabular method for nth degree polynomials. So it's a very useful tool. But now that I've got that out of the way, let's see, the integral of cosine x is sine x. And the integral of this x sine x is, let's see, negative x cosine x plus sine x. And hopefully I don't get too bad on space here. Let me draw a little wall. Now the integral of this y squared with respect to x is x times y squared, because this is just y squared times the integral of dx, and the integral of dx is x. So plus x times y squared. That's the first part, but we also have this unknown function, this constant, which is a single variable function of y. Now, like I mentioned in the last video, this constant of y is equal to the integral of this m of xy. So in this case, I'm going to circle in red this 2xy minus our partial with respect to y of what we got in the first integral. So 2xy minus partial with respect to y of sine x. I'm gonna go evaluate all this. Sine x plus x cosine x plus x cosine x minus sine x let's see, minus sine x plus x times y squared plus x times y squared with respect to y. So that's what this this constant function of y is equal to. Let me see if I can actually write all this to the side. Plus xy squared dy. Alright, so I wrote all this in a single file format. As I've been making these videos, that's one of the hardest things that I've had to deal with, is just spacing, and I'm not used to writing on a touch screen. My handwriting I don't think is the neatest, but this I think is legible. So our unknown constant of y is equal to this integral right here, and based on experience, I'm willing to bet that this integral might be equal to 0, which is why I said if you take the hairier integral at first, it'll make things a little bit tougher in the short run, but things will be easier in the long run. And if it's not 0, it's going to be a very simple integral to take. I guarantee it. I think anybody in a first semester calculus should be able to handle the integral that will result from this. But nonetheless, let's evaluate this. So c of y is equal to the integral of all of this. So that would be equal to the integral of 2xy, and I hope my partial sign doesn't look too much like my number 2, minus, and my partial with respect to y of sine x, that goes away because that's a constant function. My partial with respect to y of x cosine x goes away, thank God, otherwise that'd be a product rule right there. And same thing with this sine x, this minus sine x, it also goes away. But my partial with respect to y of xy squared, it stays. And that is, okay, x times partial with respect to y of y squared dy. And I'm doing a little bit more than necessary here, but it's really to show just the whole process of it all. So this would simplify to 2xy minus 2xy dy, and that's clearly 0. And in this case, well, you'd end up with the 0 times dy, and that's 0. Don't let this confuse you, that this is not equal to a constant of integration. I know many times I've said that the integral of 0 is your constant of integration, but that's only the case when you're multiplying, or when you're integrating 0 but you're not multiplying it by a differential, just the flat out integral of 0. And that sounds a little bit like sketchy, a little bit cliche, but the integral of 0 times dy is 0, because dy, if it gets multiplied by 0, it just becomes 0. So the final solution now to the differential equation is, what did I get here after I integrated this? Let's see. Oh yeah, the final solution to this differential equation is sine x. The final solution to this differential equation is sine x plus x cosine x minus sine x plus, oh man, I'm running out of space here. Let me express the final solution on the next slide after erasing this. So hopefully you kept up with everything in the previous slides, and the final solution to this differential equation is simply the integral of this with respect to x. So that was sine x plus x cosine x minus sine x plus x y squared equals c.